Hello everyone. Thank you for attending this talk. I'm Jérémy Charlier. I'm an AI scientist at the National Bank of Canada. And today I would like to discuss about VecHGrad for solving accurately tensor decomposition. I divided the talk into four main sections. First, I will introduce the context and the motivation, and then I will present the research question. We will move on to the proposed method, VecHGrad, where I will give some key definition and then I will explain VecHGrad for solving accurately tensor decomposition. I will present some of the results of our experiment and then I will conclude. Let's move on to the context and motivation. Every machine learning approach requires the minimization of a loss function. To minimize the loss function, there exist different approaches. The most popular techniques are stochastic gradient descent and ADAM. These techniques rely on gradient descent. So as pictured here on the graph is that you start from an initial guess of the optimal solution, you compute the gradient, and then you take the descent direction. And then you start again, where you compute the new gradient of the new intermediate solution, you take the descent direction, and then you go on and go on until you reach the optimal solution. However, these gradient descents are not always the most efficient. They do not necessarily lead to the smallest minimization error at convergence. And this is especially true when we are considering tensor decomposition. As a reminder, a tensor is simply a multidimensional array. And when you are using tensor and you are applying a decomposition and you want to solve it with a gradient descent, sometimes you don't reach the smallest local minima you want to achieve. So this brings the research question on how can we solve efficiently and accurately high-order tensor decomposition for which most of the machine learning and deep learning state-of-the-art optimizers fail. To answer to that question, we will introduce our new resolution algorithm VecHGrad, and we will demonstrate the superior accuracy of VecHGrad at convergence. Let's move on to some definitions. So for those who are not familiar with tensors, tensors have a solid theoretical framework where they rely on linear algebra. So with linear algebra, you can describe the properties of tensors, such as the rank of a tensor. So the rank of a tensor is similar to the rank of a matrix. The difference between the two is that the rank of a tensor is not unique. You can also compute the norm of a tensor, so you can compare different tensors based on their norms. And when you are talking about tensors, what you want to do is that the tensor contains your original dataset. And you want to highlight latent factors of your dataset. So you can decompose the original datasets. You can factorize the original datasets according to different decomposition to highlight different patterns which are not directly observable. So you transform the initial data to observe non-observable patterns. You can do it according to different decomposition. Here you have the three main decomposition, which is the CP decomposition or the DEDICOM decomposition and the paradox 2 decomposition, where you can see that the original tensor on the left part is decomposed according different linear algebra operation. So let's move on to VecHGrad for solving accurately tensor decomposition. So we start first by the definition of our loss function. So we consider the norm of the tensor. So we want to minimize the norm between the original tensor and the tensor based on the tensor decomposition. So the original tensor x is known, and the approximated tensor, the tensor inherited from the decomposition on the right part, is a tensor that is built and optimized. You have to perform a minimization problem on x hat to find the optimal solution that is capable to, once you reconstruct the tensor based on the decomposition equation, you have a solution that's close to the original tensor. So we want to find the optimal solution of the loss function, such as f to x star equal to 0. In other words, we want to find a norm between x and x hat that is almost the same. How can we do that? So we first start by flattening all the entries of the decomposed tensor. So instead of having a tensor representation of our problem, we stacked all the numbers and all the entries one behind another. And so we end up having a very long vector containing all the entries of the tensor. And in the process, you start first by a random guess of the solution, and then you update iteratively according a numerical optimizer. Here, for instance, you have the Newton update. However, if you are using the Newton update, then there are problems arise. Noticeably, the Newton method is not globally convergent. So if you are using the standard equation of the Newton method pictured here on the right side of the slide, you can have diverging solution. So we used and defined a line search according to Strong-Wolf's condition. Here we have a set of 3 equations for which, when you apply these conditions, then the Newton method becomes globally convergent. And these sets of equations helps to find what we call the parameters alpha. In machine learning, it's commonly known as the learning rate. So here we do not have a fixed learning rate. We have a learning rate that's updated iteratively at each step of the optimization process. Once the method is globally convergent, you have a second difficulty, which is the Newton method requires to compute the exact inverse of the Hessian matrix. However, here we are dealing with tensors, so we have a very large dataset, so it's numerically challenging. And so a way of bypassing this complexity is to use a conjugate gradient loop to approximate the exact inverse of the Hessian matrix. And we approximate it with a diagonal approximation in our algorithm. In our algorithm, we are speaking about tensor and tensor decomposition, and we have a loss function, but we also have to define the gradient of the loss function. Here we define the approximated gradient according the equation picture here. So we don't use an exact solution of an exact solution of the gradient. Why we did that is because in our experiment we really want to have only 2 parameters on which we play: the numerical optimizer and the tensor decomposition equation. By using the approximate gradient, we are able to use the same formula for all the tensor decomposition equations. So we just have to change only the decomposition equations. We do not have to change the gradient formulation. And since we are here using an approximate gradient, we are introducing numerical errors. And normally in linear algebra, it does not make any sense to compute a Hessian matrix. But since here we introduce numerical error, experimentally, we can observe that the Hessian matrix is not null, even though that we are speaking just of linear algebra here. So we also ask to we also have to compute the inverse of the Hessian matrix. And we compute it only based on information of the approximate gradient. So it means that here, by using the conjugate gradient loop and information contained in approximate gradient, we are able to bypass the difficulties of the computation of the Hessian matrix and second derivatives. So we reach an iterative update rule for the tensor decomposition, where you compute the new iterate based on the previous iterate plus the learning rate inherited from the line search using Strong-Wolf's condition and the descent direction. Here we summarize the approach of VecHGrad for tensor decomposition. So first we choose a tensor decomposition equation. Then we randomly guess the initial solution of the approximated tensor. Then we select the loss function. In our experiments, we consider the norm function. We compute the gradient. We fixed the initial descent direction equal to minus the gradient. We compute the approximation of the inverse of the Hessian matrix using the conjugate gradient loop. And at the end of the process, we get our diagonal approximation. We perform the line search to obtain the machine learning rate, and at the end we get the iterative update where we compute the new intermediate solution based on the previous one plus the learning rate times the descent direction, and we repeat this loop until we reach a maximum number of iterations or any other defined condition. Let's move on to the experiment. So in our experiments, we want to investigate the convergence rate of VecHGrad in comparison to other machine learning optimizers, such as Stochastic Gradient Descent, Nesterov Accelerated Gradient, Adam RMSProp, VecHGrad, or Limited BFGS. Since we are speaking of linear algebra, we also have to compare our results with linear algebra optimizers such as alternating least square or non-linear conjugate gradient. We performed our experiments on 5 different public datasets, here presented here in the table, where we have C4 dataset, MNIST, COCO, LFW, and we performed the experiment according to 3 tensor decomposition previously presented: CP, DEDICOM, and PyTurk2. All our datasets that we are using for the experiments is image-based datasets. So an image is a matrix. So how can we put a matrix in a tensor? So each image consists of 3 colors channels. So you have red, green, and blue. So in the tensor, so you have, if you follow the matrix representation of red, green, and blue, you have 3 matrices. And so we can stack one matrix behind another. And so we have each image can then store in a third order tensor. And once we have this third order tensor, we can decompose the image. Why doing that on images? It's because it allows intuitive interpretation of the results. Here, if we are focusing on the visual observation, we can see that Nag and Saga, at the end of the minimization problem, we are not able to observe the bus in London. So it means that even though these optimizers converged, the solution we got is clearly not satisfying because it's still just noise. Other optimizers such as SGD, Adam, and VecHGrad, which are quite popular, here you can guess the shape of the bus, but it's mostly it's very blurry. And finally, like the last optimizers that shows for which we are capable to find back the original image are ALS, RMSProp, VecHGrad, LBFGS, and NCG. So let's move on to a deeper overview of the quantitative results. So if we consider the errors at convergence between the optimizers, here we are presenting and discussing the results for the Paratuk-2 tensor decomposition, but we observed a similar trends for other decompositions. So here you can see that if we are considering errors at convergence, VecHGrad gives the best accuracy. So VecHGrad gives the smallest errors at convergence. Then we can observe that RMSProp is quite close as well. The level of errors at the end of the minimization problem are fairly small. It's what we observed before, where the level of details of the bus with VecHGrad and RMSProp was quite high. Surprisingly, here we can see that LBFGS, we were expecting to have better results, but since we used a public implementation in Julia, it's probably why here we did not have the results we expected, especially because LBFGS is one of the mostly used technique for numerical optimization. And another comment is that SGD and ADAM here also performs quite well, and we can see that depending on the datasets, either SGD or ADAM are quite close to each other. If we move on to other observation, we can see that here NAG and Saga they are not able to find an optimal solution. The level of errors at the end of convergence is quite high. We can do another observation on NCG where we can see that depending on the dataset, sometimes we obtain a diverging solution. So NCG is not always stable, especially for Paratuk decomposition, which is quite complex numerically because of the linear algebra computation involved. If we mention the computation, calculation times for the computation and to reach the convergence, it's very important here to analyze this table with the previous results, because previously we saw that NAG was not satisfying in terms of errors at convergence, but you can see here that NAG is the algorithm that converges the fastest. So here you have the fastest the solution, but the solution you get is, if you consider the image of the bus, you are not able to find back the image of the bus. It was just simply noise. And if we consider other algorithm here, RMSProp and VecHGrad, we can see that RMSProp, which is just based on gradient information, and VecHGrad that's using a Hessian approximation, we can see that in terms of computational times, these two algorithms are very close. So finally, I would like to conclude. So we introduce VecHGrad for solving accurately tensor decomposition. In our experiments, we highlight the performance of different popular machine learning optimizer. We underline the performance of VecHGrad on 5 different public datasets. Future work, we will convert the code in Python. We'll move from a Julia implementation to a Python implementation to use our numerical optimizer for machine learning algorithm and to integrate it in a deep learning framework. I thank you all for your attention. Here are my mail address. You can contact me if you have any question. I will be happy to answer any of your questions.